Okay, so how is everyone today?
Cold.
Cold?
Very cold.
Okay, well, can't fix that. So the exam is tonight.
Yeah.
Yeah. Couple comments to make sure it's clear. So today's the 15th, exam day. Terrific. Oh, I forgot what I was saying. Oh yeah, the room. So I sent a message about it, but I'll write it here also. Is that you need to look in the grade book. You've got a grade that is named midterm room, like that. It's in the e-learning grade book. So that's the room that you're in. Also, in that same message, I sent a link to UTD's map thing. Good. So I sent a list of supplies. You need to bring your UTD photo ID, a calculator, scientific, non-plotting, non-symbolic calculator, and you can bring a little sheet of paper that has just the numbers of the exercises that you intend to redo, but it can't have any notes or what have you on it. Any questions about that? Yes?
So there's 20 problems. They said that were over our Wexes.
No, not exactly. Rather, there's going to be so there's 3 mandatory problems. Mandatory. There's going to be 3 of those. So you can think of it like a quiz with 3 questions to that extent. And then there'll be a page that says something like beyond this is the redo section, and you're permitted to select up to 13. So I don't remember exactly how many there are, but there's something like 25 choices. You choose up to 13. Realistically, I'd be surprised if anyone did 13 redos and did them all well. But I'm willing to be surprised. So more likely is that maybe you do something like maybe 8 of the redos realistically. Good. Other questions? So in case it wasn't clear, the redo section and the material covers Wexes up to and including Wex 20, those ones. And you might say, oh, well, that's kind of a sharp turnaround on those 20s. Okay, no dispute. But the thing is it was the choice of, well, are you gonna turn in the 20s? So the answer to that is yes. And then are they going to be on just the final or for redo, or the midterm and the final for redo? So I decided that the more generous one was both. Did you have a question?
Yeah, I just answered my own question because when I looked last night, Wex 203 hadn't been graded yet, but it's there now.
Okay. All right. Other questions? All right. Good. So we've been talking about functions, and we're still talking about functions. For example, just to name some specific cases, we have squaring. And we have square root. So if, for the squaring function, if I write f of x is x squared, and the square root function g of x is square root x, then respectively, these plot in the following way. So the squaring function plots as a parabola, and the square root function like so. And what I'd like for you to observe about the squaring function is it has kind of two halves, right? Like a left side and a right side. And what this square root part is it's basically exactly the same as the right side. But it doesn't have a counterpart, in the sense that if you reflect this one that way, you get that one. But if you reflect this one down, there's nothing down there. So that is a visualization of the following kind of thing that I've been trying to say as many times as possible all semester long. If you take an x and you square it first, and then after that you compute square root, what do you get? Which one? You get absolute value of x. You don't get x back. In the end, the fact that these two pictures are dissimilar in the sense that this one kind of has two halves, but that one is sort of like missing a half. That's the reason why. Well, it's not the reason why, but the reason why this is absolute value is the same reason why this one only has half. Whereas if you do this in the other order, so what I want you to observe is that there's two things here, squaring and square root, and for this, you're squaring first, and after you do that, you compute square root. But what if we reverse the order of those things and say that, well, let's compute square root first, and after we've done that, let's square? What's the answer? Just x. And you might say something like, oh, come on now. Come on. Well, the reason why absolute value is not necessary here is because consider, notice that the square root is being computed first. So what needs to be true about x? It has to be greater or equal to 0. Otherwise, you couldn't even get started. Right? You couldn't even begin. As a result, you could write an absolute value there, but it would be superfluous because from the outset, x was greater or equal to 0, so absolute value is not necessary. All right, and generally speaking, if we say let n, little n, be in the naturals with n greater than or equal to 2, then generally the pattern is this table. So here we'll consider the order that we're doing things in. So we'll say that this one is you square first. So that's what the first row is, and the second row is going to be if we compute square root first. No, I don't want square. Sorry. Rather, I want to. Where's the eraser? Rather, I want to say just exponent, not necessarily square. So we'll raise to an exponent first. And then we'll do nth root first for this one. And then concerning n, there'll be two possibilities that n is even and n is odd. Then by exponent first, I mean that we're going to take an x and raise it to exponent n, and then after we've done that, we're going to compute the nth root. So that's just like this, because remember, square root is which radical? radical 2, right? So when you don't put the name there, it's understood to be 2. So what's the nth root of x to the n? It is, just like that one,
Oh,
absolute value of x. Okay. And if we switch the order of those around and say, well, let's compute nth root first. And after we've computed nth root, let's raise it to exponent n. Then what's the answer? Just x. It has to be just x because we're in the even column. And because x is the input to an even radical, that means that x can't be negative. All right. So then what about this case? If n is odd and we raise it to exponent n first, and then follow that up with a radical, what's the answer? Yeah, when n is odd. Just x. So an example of this would be, what if we take negative 2 and raise it to exponent 3? What if we cube negative 2? What do you get? Well, that'd be negative 2 multiplied by negative 2, which is positive 4, multiplied by one more negative 2, that'd be negative 8. And then if we compute the cube root of that, what do we get? What's the cube root of negative 8? Negative 2. So have a look. When you do that with an odd number like 3, then there's no absolute value. Interesting. And what if we have an odd n, and we compute nth root first, and then after that we raise to exponent n? Then what's the answer? Just x. So there's kind of like 4 possibilities, depending on the order that you do the square, the exponent and the radical, and also whether or not the exponent and radical themselves are even or odd. And because there's 4 possibilities, and 3 out of the 4 are just x, to me that kind of is the reason. It seems to me why so many students are resistant to that one. After all, it's just 1 out of the 4 cases. But in the end, even though it's just 1 out of the 4 cases, it ends up coming up like probably like at least 3 out of 4 times, because square roots are so much more common in practice than cube roots. It's just the way it is. Any question about this? So again, I want to emphasize that the order matters, the order in which you do things. And the same kind of, you can imagine the following. Suppose we all go into business and we start a doll manufacturing business, and maybe it has like workstations, and maybe there's a workstation that puts on left shoes, and another workstation that puts on right shoes, and a workstation that puts on left socks. So where the finished product is concerned, can you tell if the left shoe was put on first or the right shoe? Can you tell? Nah, you can't just look at it. You can't just like look at your neighbor, say, and just inspect them and say, oh, I see that you put your left shoe on first. You can't do that. But what about so in that sense, the order of the left shoe station and the right shoe station don't matter. But what about the left sock and the left shoe? Does that order matter? Yeah, right. It does, because you can look at your neighbor and say, I can see that you put your left sock on before your left shoe. So the order really does matter, and this is just one example of that. Any question about this? All right. So we've been talking about functions, and again, I want to stress the mental model. for functions. In the first place, a function is like a machine. And what I want you to take away from that word is that this means a deterministic machine. What does that mean, deterministic? Well, it might help to give an example of something that is non-deterministic. So you can imagine something like a random number generator, where you push a button and then a screen pops up a number and you can look at it. So if you press it once, click, and then up comes, like number 5. Okay. If you press the button again, do you expect to see a 5 again? No, because it's a random number generator. There might be a 5 again, but if you click it again, you might get a 5 million. Who knows? It's a random number generator. That's a non-deterministic thing. A deterministic machine is a machine where you give it an input, and it will always produce exactly the same output, no matter how many times you give that input. Okay, so it's a machine. It accepts inputs. What's the name of the input set? Domain. So inputs come from the domain. From inputs, it produces outputs. And what is the name of the output set?
Range.
The range. From the range. And furthermore, every input produces exactly one. Exact has a T in it, exactly one output. And again, to stress the squaring and square root thing, when you square things, so for example, 8 and negative 8, so if this is the squaring function, then they both go to 64, right? So does this satisfy the rule that that every input produces exactly one output? It does, right? Because visually what that means is that there's one arrow leaving all of these. Notably, that doesn't mean that there's one arrow arriving. The definition says nothing about that. So, now, for square root, I could ask, what's the square root of 64? It's 8, right? And is it proper to say that the square root of 64 is positive or negative 8? No. Why not? Yeah, it's just 8. Why is it just 8?
Because there's only be one output.
Yeah, because if you input 64, then it's only permitted that there should be one output, not two of them. Okay. Good. Any question about this? All right. So now, here we've got an idea. What about the following function? Suppose we've got a function a, b, c, d, and a domain a, b, c, d, and a range 1, 2, 3. And suppose that this is the mapping. So a to 2, b to 3, c to 1, and how about d to 2? All right. So this thing that I've drawn, is it a function? It is. Right. It is because there's one arrow leaving everything in the domain. So suppose that I wrap this all up in a neat bow and say that this is function f. Okay, then I could ask, please evaluate f evaluated at b. So what's the answer? 3, right? Which is just to say, you know, you find b in the domain and then you just okay, 3. Any question about that one? Okay. How about solve? Solve f of x is equal to 1 for x. Now what's being asked?
Define what x is.
Right. So to restate the first question, the question was, if you start at b, where do you end up? At 3. And then the current question is that is saying that, well, if you ended up at 1, where did you start? Well, you started at c, right? All right. Here's something slightly interesting. How about solve f of x is equal to 2 for x. How about that? Right. So again, this is sort of like saying, if you ended up at 2, then where did you start? Well, in fact, you could have started in 2 different places. You could have started at A, or you could have started at D. That's interesting. All right. So here, what I want you to do is I want you to redraw. So redraw this thing, but with the arrows turned around. So with the arrows pointing the other way. Okay. Okay. So I just, I did it. Okay, so then now, here's my question. Is that, is this thing that we're looking at, is it a function?
No.
Why not? Right. Because now, remember, the rule to be a function is that every input must have one arrow leaving it. But this one has 2 arrows leaving it. So this is not a function. So an example of this, of such a thing, would be that the squaring function will take 8 and -8 both to 64. Right, but if you turn it around, if you just take this and redraw everything except make the arrows point the other way, then the result is not a function. So here, I'd like for you to think of it like this. What if you're, say, up here, and this is a big building, a building-sized function, and there you are. Okay, and you know everything that's exactly how this machine is made on the inside, but you can't see it. And you've got your colleague or whatever over here, and you're right here. Suppose that you witness a 1 come out. Do you know what was put in for sure? Yeah. What must have been put in if you witness a 1 come out? A C. Nothing else could have produced a 1. Similarly, or alternatively, what if you witness a 2 come out? Are you for certain what was put in uniquely? No, right? Because it could have been an A or a D. Similarly, if you're here standing on the output side of the squaring function, and you witness a 64 come out, are you for sure what was put in? No, you're not, because it could have been an 8 or a -8. So what we want, what we're going to currently focus on, we want to focus on the kinds of functions that you can turn them around and they're still functions. So to be a function, there must be 1 arrow leaving everything in the domain, exactly 1 arrow. But what will be required if we want to be able to copy that, turn all the arrows around and make them point the other way, and the result is still a function? What will be necessary then?
That every output only has 1 input.
Right. Which is to say that, to be a function, only 1 arrow, exactly 1 arrow must leave. To be this new kind of thing that we're talking about, exactly 1 arrow must arrive. Okay, so if both of those are true, then we have the kind of thing we're talking about. So let's draw one of those. Oops. So here's an example. So, is it a function? Okay, why is it a function?
It's a function because there's only 1 arrow leaving each.
Right. 1 arrow leaving A, 1 leaving B, 1 leaving C. Okay. So now copy it, make a new version of it, but make the arrows point the other way. Oh, whoops. Just imagine that's not there. So, so I made the arrows point the other way. Is this thing a function? Yes, because now there's 1 arrow leaving. And what I want you to observe is that what that means is that notice for this function. If you're over here and you witness a 1 come out, are you for sure what was put in?
Yes.
How about a 2?
Yes.
How about a 3?
Yes.
Yeah. You know exactly how it works. So in some sense, what I want you to have an idea is that well, you could be playing ping pong with your buddy there. Is that they could put say an A in, like A goes in, blip, and then the 3 comes out. And then you could just push the 3 back in, and then whoop, the A comes back out on the other side. Whereas this kind of machine can't do that because if a 2 comes out and you try to push it back into the machine, then it gets all the works. The insides get all gummed and messed up. Won't work. Okay, So these kinds of functions, the functions that do this, are so special that they have a name. So such. So this is a function. And the reverse is also a function. So such functions are special, and they have a name. They are called one-to-one. But that's what the textbook calls them, but I don't really like that name, honestly. So there's math is a culture like anything else, and so things slowly change over time. So there's like this age line I would estimate to be somewhere between like 45 and 50 years old, where if you're an English-speaking mathematician and you're say about 45 or older, you're going to call this one-to-one, but everybody else in the whole world, all the cool kids, are going to call it something else. So this is also known as injective. So the reason why I don't like one-to-one, that name, because it's kind of confusing, because you've got to keep track that one arrow leaving, that's what it means to be a function. And if you have a function such that it's always the case that one arrow is arriving, that's what it means to be a one-to-one function. So there's too many ones in all those words. So algebraically, f is injective. Injective means f of a equal f of b implies a equal b. So that's the kind of math definition that only a mathematician could love. So let me kind of explain what this is saying. It's saying that suppose that you witness two outputs. So you observe this first, and then you observe that, and they're the same. So what I mean is that it's like you're standing at the output of a machine, and say you watch a 5 come out, and then who knows what happens, and then a little bit later you watch another 5 come out. Well, if that machine is injective, what that's saying is that both of the times that you saw a 5 come out, the same input must have been provided, because there's only one way to get a 5. So if you observe this and then that, and they are the same, then the same input was given. Twice. So the squaring function is not injective, because if you witness a 49 come out, then later you witness 49 come out again, then is it the case that the same input must have been provided twice? If you're on the output side of the squaring function and you see a 49 come out? No, right? Because maybe the first time it was 7, and the next time the input was -7. You don't know. As a result, it's not injective. So geometrically, geometrically, to be a function, which is to say that you have one arrow one arrow is leaving. Here's two possibilities. So, for example, here's a function here. Okay. Then I could ask something like, well, here's an input because the horizontal axis is the input axis. So that's an input. What is the output? And how do you figure it out? Is that input even in the domain? How do you tell? Well, remember, this is the, you can either view it as the mashing thing, where we said, imagine that we paint the plot and then squish it. What part of the horizontal axis gets painted? Or you can do the vertical line thing and say, well, does that vertical line cross the graph? It does, right there, right? So that's in the domain, and that's the input, and therefore this is the output. So input, output. Whereas let's consider this drawing. So, for example, here's a point right there. And now, concerning this thing that I've drawn here, is this point that I've selected in the domain? Which is to say, if we take the plot there of that circle thing and then paint it and then mash it onto the horizontal axis, will that green point be one of the points that gets painted? Yeah. And alternatively, this vertical line that goes through that point, does it touch the graph? In fact, twice, right? So it touches twice. And so what that's saying is that this input produces two outputs, right? Which is to say that that thing right there is the input, and these two things are outputs. So how about it? Is this a circle that we've drawn here? Is that a function? What must be true about functions? How many outputs are permitted? One. So is this a function? It's not. So, well, this consideration, this visual consideration, is called the vertical line test for a function. Because, well, for example, this point right here, do you notice that it intersects the plot there 0 times? That means it's not in the domain. That's okay. And do you observe that every vertical line touches the plot exactly once? What that's telling you is that every input produces either no output because it's not in the domain, or one output. That's called the vertical line test for a function. So every vertical line must intersect two possibilities. It could be 0 times, so in that case, what does that mean about the point in question? It's just not in the domain. or one time, which means that it is in the domain and it produces exactly one output. So that's what it means when you're making a plot to translate it into this language, that exactly one arrow is leaving. Now we want to say, well, how do we make it to where one arrow is arriving? Okay. So to be injective, well, here's three pictures now. Okay. So how about something like this? So that one, that one, and that one. So we're almost done here. So now, the question is that is it the case that every input has a well, is it the case that it's injective? So instead of using vertical lines, what are we going to use? Horizontal lines. So for example, how many intersections does that one have? None. So that means that, that's not in the what? The range, right? It's not in the range. And then if I come up here, I could ask about this point. Is that point in the range? Yes, because there's one intersection. So what input could I use to get that output right there? What input gives it to me? Remember, inputs are on the horizontal axis. Well, you march over to that intersection, and then it tells you that that input produces that output. Do you observe that every horizontal line crosses 0 or 1 times for this one? So this is injective. We're almost done, almost done. How about this one? Is this one injective? No, because, well, how many times does this one intersect? 0, right? So that's okay. What about that one? How many times does that one intersect? Once. So does that mean it's injective? No, because we've got a quantifier that says every, right? Every. So, for example, that one. Notice that that point in the range is achievable by 2 inputs. Finally, and this is the one that trips students up all the time. So this is not injective. But this last one, is this last one injective? No. It's not. Why is it not injective? It's not a function. Is this a red apple?
No.
It's clearly red. Oh, but it's not an apple, right? Is this an injective function?
No, it's not.
No, because it's not a function. All right. Have a nice, I'll see you tonight maybe at the exam.
Yeah.